All right. Good evening, everyone, and welcome to tonight's class. We're going to be making a continuation of the previous class, which was on calculus. So in today's class, we want to delve deeper into more of calculus. I'm really excited about today's class because there are so many things we want to talk about. And guys, you have to be with your writing materials because I really want you guys to flow along. I want to be very calm. I don't want to rush this too much. I want to bring this at a level everyone can relate to. I don't want, the focus is not on covering volume, but rather on ensuring that at the end of today's class, everyone was able to flow along and was able to get the best from the class. Now, I need to say this. Some of the aspects we'll be dealing with today is woven around some aspect of trigonometry, which I believe I have personally taught you that, and majorly you'll be making use of the identities that we dealt with under trigonometry, and that's the compound angles at some point, the sum and difference formula. So we'll be using many of all these things in today's work, and this makes it very important for everyone to go back to ensuring that they very much learn all these identities. So I also want to say that because of the nature of calculus, most of the things we are doing are continuous. So it would be very hard for you to flow at the midpoint of the class. And that's why I always implore you to try and join early so that we can flow together. If you come at the middle of the class, many of the things we would have said prior to your coming will be key to you understanding what we're discussing. So I believe we are all available, and I believe we are set for today's class. It's going to be basic. We're going to ensure we try our best to bring it down to your level. So yesterday we did something around range and domain, and I believe we're all able to understand the concept around those subjects. Now, ideally, following the note you have, we're supposed to be dealing with types of functions, in which we have functions based on elements, the one-to-one function, any-to-one function, onto function, into function. And then we also have functions based on equation. We have the identity function, the linear function, quadratic function, cubic function, polynomial function. We have also functions based on the range, where we have the modulus function, the signum function, the periodic function, the composite function, rational function, even and odd function, the greatest integer function. Also, I can see right in your notes, we have functions based on domain, where we have the algebraic function, trigonometric function, logarithm function, and exponential function. Now, we will not be doing so much around the explanations around this because I believe this is something we have dealt with, a lot of them or some of them, and it's you could read up on it. So in all these functions, the two I will be specifying on this night, and just briefly, is the inverse function and the composite function. And that's just to ensure that it's more like just a revision of what we have done. I want to ensure that there's no one year that is still lacking when it comes to finding the inverse function. So I will just do that briefly. And of course, if you are good at it, you will just get more knowledge on that. So this is I will just be solving about just a few, very few number of examples. So we have this function. I want to quickly explain inverse function. And if you have known it, this will just be as a revision. So imagine we have a function given like this, f of x being equals to x minus 1 over x minus 2. and you are asked to find the inverse function. This is the way, in many cases, you would see it given. So what you want to do is to basically follow these 4 different steps that I'll be giving you. Just 4 different steps. Step 1, 2, 3, 4. And you will always get your answer. Now, the very first step is for you to change the f of x to y. That means you change this to it looking like a linear function. Step 1 is make this a linear function. And that will be you changing f of x to y. So step 1 is just doing this, which I believe everybody can do. Now, step 2 is for you to exchange your x for y and your y for x. So wherever you see y, you put in x. Wherever you see x, you put in y. Of course, we're not doing so much around this. I just want to do this briefly. Then we're going into deeper concepts in calculus this night. It's going to be quite very interesting. And I want you to really, really pay attention. This is just revision, just to ensure that I don't leave this unturned in your notes. Now, what you want to do next is to change wherever you see y, you want to change it to x, and wherever you see x, you want to change it to y. So I can see y right here. So I change this to y. I just change it. I will just write, instead of writing y, now I'll be writing x. I see x here. Instead of writing x, I'll be writing y. So I'll be writing it like this. That's the next step. And then step number 3 is for you to now try and make, you see, we have done step 1, we made it linear. Step 2, we swapped x for y and y for x. Step 3, we now want to make y the subject of formula now. So whatever I have here, I want to make y the subject of formula. And the best way to do this with the particular function we have here is for you to cross multiply all this, and then you'll be having x into bracket y minus 2 equals to y minus 1. So you want to bring everything all together, then rearrange in such a way that you can be able to make y the subject of formula. So when I do this, I have xy minus 2x equals to y minus 1. All right, and what I have right here is xy minus y. Of course, you know what I'm trying to do here. I'm trying to bring up the y to one side and the other variables to another side. So I have equals to 2x minus 1. So here I can obviously make y subject of formula, y into bracket x minus 1. And then I have equals to 2x minus 1. So what I have as a result of this is my y now will be equals to 2x minus 1 over x minus 1. So you can see I have done 3 of the steps. Step 1 was to make it linear. Step 2, swap x for y and y for x. Step 3, make y the subject of formula, which is what we can see. Now the step 4, which is the last step, is for you to change y now to what you have here. So I will change y to f inverse of x. That's all. That's basically all. So this is the 4 different steps for you to, you can never go wrong if you follow these steps in the right way. So let's leave this quickly because we don't have much time. We want to focus. I believe everybody could relate to this. And if you could not, that's a good revision for you. So we want to go into composite function just as a revision also. Let me try and remind whoever has forgotten. So we have these 2 different functions. We have, of course, when you're dealing with composite function, another name for composite function is function of the function. So composite function, you would never just have one function when dealing with composite function. You always have 2 different functions. So we have f of x now being given as 1 plus 2x. And then we have also another function. This is the, we're calling this one gx. This will be 1 plus x. All right, 1 plus x right there. So what we are told to find is all this. We're told to find the first one. We're told to find GOF 1 over 2. And then number 2, we are told to find FOG 1 over 2. And then number 3, we're told to find the inverse of the composite function of FG, and then the last one is the inverse of composite function of GF. So let's try and see how we're going to do this very quickly. So we have this function right here. What do you want to do first? This thing is so simple and straightforward. You don't have to sweat over anything. What you just have to do, you are doing here is embedding one function into another function. So when you have GUF, before I start talking about GUF, let me talk about GUFX. So let me first talk about GOFX. Of course, you know that the meaning of this half here means wherever I saw X, I'll be putting the half. It could be anything here. They could put GOF2. If I told you to find GOF2, that means I'm saying wherever you see X, just fixing 2. So let's try and even find GOFX. What will it be? What's the composite function first before we try to put in X as 1 over 2? So the composite function when you're solving GOF, this means that the first function that comes is the parent function, while the second function is the child. So in this case now, F is the child, so we're embedding F inside G. So this is G. So G is the parent now. So let's say I have G as 1 plus X. All right, I'm trying to get the answer for the composite function. So what I want to do next is to, wherever I see X, everywhere I see X, I want to change it now to my F, to my function F. So wherever I see X now, we put in the function F there because I'm embedding F inside G. So I see this here, I'm having this. So this is basically GOFX. This is it right here. So, but this was not what they told me to find. They told me to find GOF half. So what I want to do is to go on to fixing now. Wherever I see X now, I want to put in half there. So I'll be having 1 over 1 plus 2 now half. All right, just basically substitution. We're substituting 1 over 2 for X. So this is 1 over 1 plus 1 plus. This will cancel this, will be left to 1 plus 1. All right, that will be 1 over 1 plus 2, which is what? 1 over 3. And that's my answer. Straightforward. Nothing to talk about. That's just it. So let's try and do FOG half. So for FOG half, I think I can take this off. Okay, let me try and still use this space. So for us to find FOG half, I'm interested in what is even FOGX. All right. To find FOGX, you have to understand that in this case, F is the parent and G is the child. So I'm embedding G inside F. So what is my F first initially? This is 1 plus 2x. So let me write 1 plus 2x here initially. So the meaning of when I'm trying to find my composite function is that wherever I see x now, we put in the function g. So I have the function g right here, 1 over 1 plus x. This is the function g. Look at it right here. All right. So this is my FOGX. That's just it. This is my composite function, f being the parent and g being the child. So, but let me go on to now try and find FOG half. That means wherever I see x now, I have to embed half in there. So I have 1 plus 2, 1 over 1 plus half. All right, I'm sure you can relate to that. So what do you notice is going on here? I would obviously be having 1 plus, this would be 1 plus 2, 1 over 1 plus 1 over 2 is 3 over 2. I'm sure you understand 1 plus 1 over 2 is 3 over 2. So this will be 3 over 2. All right. So let's take this off, and then you will be able to see what does this give you. We'll be having, obviously, we'll be having 1 plus, now this will turn to 1 divided by 3 over 2, which will be 1 times 2 over 3. I'm sure you understand all those arithmetic. So this will be the final answer of 1 plus 2, and then we have 2 over 3 now. 2 over 3. So this will be 1 plus 4 over 3, which will end up as 7 over 3. If you go on to do the LCM here, this will be 7 over 3. All right, so that's just basically composite function. I don't want us to spend too much time here, just a revision we are doing right now, just in case, and since I can see it's part of the preambles of what your notes as. So now the last one here, you are told to find, I think I probably will leave you to find this rest, the inverse of fg. When you found fg, we found fgx. To find the inverse, that's not supposed to be hard. So I'm not sure I would love to do this. Probably you do it yourself. Go on to make the inverse of the composite function when f was the parent and g was the child, and then make the inverse of that. It's more like saying you are having FOG x and you're finding the inverse of FOG. So you know you obviously have to go on to first find, the first thing to find is FOG x. And how do you find FOG x? I did that already. That will be 1 plus 2x. So wherever I see 2x now, wherever I see x now, I'm putting g. That'll be 1 plus x. So this is it. And if you go on to try and solve this without having the whole thing, then you would be able to, you know, you had to fix in x the other time. So don't fix in x now, just solve. That'll be 2 over 1 plus x. Solve the whole thing, make it as one fraction, and then go on to make the inverse of that using the steps I explained when we started. And that's the way you're going to be able to get that. So this is where we're going to be stopping composite function. I don't want to, again, spend too much time on this because we have so much to do. And I think this is something that many of you really understand. Now, let's run quickly to the next aspect of what we're dealing with. So, guys, brace up. This is going to be interesting. We have a lot to do. Now, again, we're going to be, something we're going to do today is that we're going to, there are some things I will not yet explain in great detail today. Like, for instance, the product rule, the chain rule. I don't want to talk about that yet. But while trying to explain the L'Hopital rule, I would have to sometimes make use of the chain rule or the product rule. So I will be solving those things using those rules. I will explain them briefly. I will not go very deep into them, but later on, probably in subsequent classes, we will talk more on product rule, chain rule. And then also these secular functions, we're going to be using them, even though we could have done that much later, but because we will have to talk about L'Hopital rule, and L'Hopital rule will require you to solve those things. So we will be talking about those things. And that's why this class is going to be quite robust. You're going to end up learning so much. Even though we'll be talking about limits, but while talking about limit, we'll also deal with product rule, chain rule, and some other things around that. So now let's go on to limits of a function. So we want to talk about limits right now, and this will break up to so many other things. So limits of a function, very, very essential to understand. If you really want to be good at solving questions around trigonometry, you want to understand limits very well. So what exactly is limit? Now, let's just write the basic notation of limit. Because when you want to talk about limit, you want to write limit. Then you want to talk about the function you are trying to get the limit of. And you must, one of the basic components of limits is that you want to talk about where the variable of the function is tending towards. So you can say, for instance, x is tending towards anything. So you can say x is tending towards, for in this particular notation, let's just write a. So this is a perfect example of how you're supposed to recognize limit. It's just, you have a function. We have been talking about functions in a while. So you have a function, it could be anything. It could be a logarithm function, it could be any type of function, algebraic function or anything. Now, you want to take the limit of this as x, this is how you say this, as x is tending towards a. Tending means just the same English word. Tending, that means x is approaching a. That means x is moving closer to a. Now, we can just decide to say, okay, let's say all this limit was equals to a, just for the sake of nomenclature. So wherever, if I wanted to talk about this limit now, I could always recognize a as the limit, as the whole limit. Now, this let's use a basic function. Let's say, for instance, we have f of x being equals to 2x plus 1, a basic function, a very simple function. Now, if I go on to say, I wanted to find the limit of this function. Let's say I want to find the limit of 2x plus 1, and I said x was tending towards 1. For instance, just like I said, x could tend towards anything. X could tend towards 0. X could tend towards 1. X could tend towards anything. Now, if x is tending towards 1 here, let's try and investigate what this actually is saying. Now, tending towards 1, there are many numbers that indicates that something is approaching 1. And you can go on to even check for maybe 0.8, 0.89, 0.90, 0.99. Then you can even have 0.999 and on and on and on. Like all these are, it's more like if you see this movement now, this movement is, they are all, you see the variation, the way it's moving, you can see it's tending, moving towards 1. All right. Now, if you go on to investigate using this function now, 2x plus 1, what you want to do in solving this is you want to say 2x plus 1. So tending towards 1, x tending towards 1. That means, for instance, let's say x was 0.9. What was the answer we got? We got the answer as 2.8. You go on to solve this, you get 2.8. A much more closeness to 1 will be 0.99, for instance. That's tending more closer to 1. And what do we get here? We got 2.98. If we have to 0.999 again, this is closer to 1 than this. Of course, this will be 2.998. One thing you can see that happens is that when x was tending towards 1, you can see that the answer, the result, is tending towards what value? Tending towards 3. That's the reason why when we are going to solve something like this, what we basically do is to just go on to fill in that value into this place. Now, we go on to say this will be, okay, I don't need to write the limit. This will be 2, 1 plus 1. That means we just fill in the value for x as 1. And this will be 2 plus 1. That will be 3, which you can see was what it was tending towards while we kept on filling in the values of different x's that were tending towards 1. So that means we can say now that the limit of f of x, this f of x being 2x plus 1, as x was tending towards 1 is equals to 3. All right? That's what we're going to say. This is basic and very, very important. Now, there are many other examples you can go on to solve, which will just for the sake of us running through something so that everybody can follow through calmly. Let's try and just do a few simple examples. Then very soon now we'll be approaching much more technical aspects of all these things. So we're going to, I'm going to ask you now to do something now. I have f of x as 3x cubed plus 5x minus 6. I also have f of x as 4x3 plus 3x minus 1. And I also have f of x as x squared plus 2x, let's say plus 11. So I want you to quickly give me the answer to all this. So let's say, for instance, x was, find the limit of this as x is tending towards 1. Find the limit of this as x is tending towards half. Find the limit of this as x was tending towards 0. So can I get answers from the class quickly? Let this be our first exercise. What do you feel is the responses to this? Find the limit of this function as x was tending towards all these things. All right. So what's the first one? What's the limit of this function when x was tending towards 1. Of course, all you have to do, the first one, what you have to just do is fixing the value of x as 1. So that means we'll be having we have 3x cubed, and that will be 3, because x was tending towards 1, 1 cubed plus 1 minus 6. That will be 3 plus 5 minus 6. That will be what? 8 minus 6. That's what? 2. So the answer to this is 2. That was the answer. So the limit of this function when x was tending towards 1 is 2. Simple. I believe everybody here can relate to that. All right. The limit of f of x as x is tending towards 2, x tending towards 1 is 2. That's why I want us to start from scratch, from the basics. So if you can understand this, then we'll build up on this. So please, if you are there, always try to attempt all these questions so that at least you gain the best knowledge. So for this one now, x is tending towards half. All you have to do is fix in half into as x. And then let's see what happens. We have, this would be 4 times 1 over 8 plus 3 over 2 minus 1. So what do you think this gives you? Of course, this will be 1 over 2. 1 over 2 plus 3 over 2 minus 1. What's the final answer there? 1 over 2 plus 3 over 2 minus 1. This will be 2, 1 plus 3 minus 2. That will be 4 minus 2 over 2. That will be 2 over 2. That's what? 1. All right? Now, did you all get this? So 1, I believe, was the limit of f of x when x was tending towards half. And what do you call, what's this one? I don't need to even do so much around this. When x is tending towards 0, all I have to do is to fix in the value of 0 there. That'll be 0 squared plus 2 times 0 plus 11. This will obviously be 11. So the limit of f of x as x was tending towards 0 is 11. All right. All of you guys got this perfectly, I believe. So this was well understood. All right. Now let's build up on this. That's the way we're going to do this. We're building up on the basic knowledge, and then we'll keep using this to advance into all the other things. So I believe now you have seen that this, you can see the basics of limits and how you solve it basically. Okay, was the second one 1 or 1.5? Somebody is writing 1.5. All right, now let's go on to talking about limits of fractional function. Fractional function. Now, fractional function in the sense that, you know, what we just solved now was a linear function. Some of them were linear. I think, do we have any linear? No, every one of them. One was cubic, a cubic polynomial function, a polynomial function of order 3, however you want to say it. Then we had, I think we had, the last one was a quadratic function. Now, what if we have fractional function? You understand what I mean by fractional function? That means the example I solved when I started this class and I wanted to explain inverse function, I wrote f of x being equals to x minus 1 over x minus 2. This is an example of a fractional function. You can see it's a fraction. You can see it. Now, this comes with a different understanding. So let's move step by step. So let's say we have fractional functions. For instance, let's say we had f of x being equals to 2x over x plus 1. All right. Now, we want to find the limit as x was tending towards, let's say we want to find the limit of this function as x was tending towards infinity. Now we're talking, the previous one we did, we mentioned x tending to half, x tending to 0, and so on. X could also, I told you already while I started, I said X could tend towards anything. So let's say X was tending towards infinity. So before we go on, let me quickly give you some properties of this infinity that we talk about. Now, when you are dealing with infinity, infinity is a number that indicates there's no boundary. So note some things. If you say infinity plus 1, it's always going to be infinity as your answer. If you say infinity minus 1 or anything related, you are also always going to have it as infinity. And also, if you have, let's say, 1 over infinity, 1 over infinity, or infinity times 1. Now, I'm using 1 here just to be basic, but it doesn't mean I meant just 1. It could be plus 10, plus 11. It could be minus 11. It could be 11 over infinity. It could be infinity times 8. It could be anything. I'm just using this basically. The answer for this one, obviously, is infinity, infinity. The answer for this particular one, this 2 is infinity. This 1 is infinity. This one is 0. So when you have something over infinity, the answer is always 0. All right? So note those things. So if you say 5 times infinity, it's infinity that is the answer. If you say 6 times infinity, infinity is the answer. If you say infinity square, that's another example, is infinity that is the answer also. All right? Infinity. So understand all these things. And when you say, now the only difference is when you are having a number over infinity, it's going to be 0. So let this stick to your mind, so that when we are solving, you are not asking how do we get 0. Once I have a number, for instance, 3 over infinity, 5 over infinity, or it could be 1 over infinity square. I'm sure you know 1 over infinity square is still going to be 0, because infinity square is infinity. So understand this basic, and then while we're solving, you don't have any issues. This is just basic knowledge around infinity, so that you don't stress yourself in trying to understand what we want to do next. So now that we're saying X is tending towards infinity, obviously, this brings a different perspective. Now, if you have to fix this directly, that means if I wanted to fix this directly inside here, let's say I want to find X tending towards infinity of this function. So obviously that means I'll just be fixing X as infinity. That means I'll be saying 2 times infinity over infinity plus 1. All right. Now, let's see exactly what I was talking about. 2 times infinity, I told you already, this is going to be infinity. All right. And infinity plus 1 is going to be what? Infinity. I said that already. So we have infinity over infinity. Now, this is what we call indeterminate form. This is the perfect understanding around indeterminate form. Indeterminate form occurs when we have a situation around infinity over infinity, or sometimes when we have 0 over 0. So those are two different, I think I need to try to explain that a bit. When we have a 0 over a 0, we say it's an example of what we call indeterminate form. So these two, just let me write this here. Indeterminate form occurs when you have situations like this, or when you have situations like this. Note that, please. This is very key to, well, don't forget we are building this knowledge. I've already explained the concept around infinity. Now, when you have situations like this, this is an example of where we say something is in indeterminate form, or maybe when you had 0 over 0. These two things sometimes used to occur while solving limits. So you need to understand how to deal with them. There are different procedures of dealing with things like this. So note that. Now, let's move on quickly. When you have a situation like this and you have infinity over infinity, This doesn't make any sense because there's nothing you want to be doing right here. Infinity over infinity, that's not an answer. You're not interested in that answer. So what you have to do, now, let me say this, because I believe I'm talking to people that are very interested in success. If you don't rush into the method that we will use when we have indeterminate form. You first want to try out the input of that thing. So don't go on to say, I see a fractional function and I want to go on to use L'Hopital rule, for instance. No. What you want to do first is to first fix in that x value inside it and check if what you had was indeterminate form. It's not every time your limit will always produce indeterminate form. Even when you have x tending to infinity, it's not every time you're going to have a situation like this. There are times when x is tending towards infinity and you will not have a situation like this. It's possible. It's very possible you have a situation like that, especially when your depending on the way your fractional function is placed. So all I'm trying to say here is don't be hasty to trying to use the techniques we use when we have indeterminate form. First fix this in, determine if it's in this form, then proceed. Now, we have seen that this is in this form now. So what are the things we have that we can do? What are the things in our toolbox for us to use to solve this? Now, as I said already, we can use two different, probably more than that exists, but in this class I will be using I'll be using almost 2 or 3 different ways of dealing with things like this. Now, look at what we have here. We have gotten here now. We know this is an example of indeterminate form. What do I want to do next? I could either use L'Hopital rule, all right, or L'Hopital rule. I believe you guys have seen that before. It's a very I could use L'Hopital rule, very simple and very straightforward. I'll be talking about that very, very soon. Or I could go on to simplify. I could go on to try and simplify. Try and simplify the function. So one of these two will always work. They both will always work in many cases, almost all cases. So look at how we're building this now. I fixed in my x as infinity. I got this indeterminate form. I won't use any of these two. I can either simplify or use L'Hopital rule. If the question says using L'Hopital rule, then you have to make sure you use L'Hopital rule, which we'll be talking about very, very soon. So, but I want to use the simplification method first. And I'll be doing that what I'll be doing for many questions tonight is that we'll use both simplification and we'll use L'Hopital rule and see they are going to get the same answer, and you guys will choose whatever you want to use if you are not asked to use a particular method. Now, how do we simplify this? The best way to simplify this at this point is to divide through by the highest power of the function. Look at the function now. We have x raised to the power 1, we have x. So obviously in this case, the highest power here is x raised to the power 1. In some cases, it may be x raised to the power 2. So what you want to do now is to divide through by x raised to the power 1. So we'll be having a new different situation. So I have limits of, as x tending towards infinity, I have, now instead of just having 2x, now I'm having 2x over x. I'm dividing through, I have x over x, I have plus 1 over x. You see how we do this? You divide all through, everything. Every single value there, you will divide through by the highest power. So the highest power was x. So I'm dividing 2x over x, x over x, 1 over x. You see how I did it? You must make sure it goes round. So now, if I go on to do this now, I'm going to be having a whole different thing. This will be 2 now over 1 plus 1 over x. All right. Now, look at what I said now. In this place now, after simplifying this, you can now go on now. This is the way you do this. You can now go on now. You have simplified this now. You can now go on now to try out fixing your x as infinity again. And that's why I told you that it's not every time you're fixing your x as infinity that you're going to be getting indeterminate form. Like now that you have simplified this and this is what you are having now. If you fix in x as infinity now, look at what you're going to get. So this obviously will be 2 over 1 plus 1 over infinity. Now, I told you 1 over infinity will always be, anything over infinity is always 0. So all this changes to 0. So I have 2 over 1 plus 0. That will be 2 over 1. That will be 2. All right. Now, I wish to introduce the concept of L'Hopital rule at this point. Look at the answer we got when we have limit of this function. We got 2 as our answer. Don't forget, when we started, we first got an indeterminate form. Then we went on now to simplify it. This was the simplification method. We can use another method I call the L'Hopital rule. Now, let's try and use the L'Hopital rule. Let's talk about what does the L'Hopital rule state. What is L'Hopital rule about? Yeah, it's a method used to evaluate limits that result in the indeterminate form. And what you basically do is that you will, after you've gotten a situation where it was an indeterminate form, you will go on now to find the derivative of both the numerator and the denominator. Let me say that more calmly. So I have a function f of x. Before it was 2x over x plus 1. I was trying to find the limit of x tending to infinity here, and I ended up getting an indeterminate form. What do I do next if I want to use L'Hopital rule? L'Hopital rule is very simple, very basic. All you have to do is go on to find the derivative of the numerator, go on to find the derivative of the denominator. And after you are done doing that, make it a new function. So let's just permit me to call this function. Let me call it, just permit me, even though I know this was f of x, permit me to call this f of x, permit me to call this g of x. So I have f of x as 2x. I have g of x, x plus 1. So if I wanted to use my L'Hopital rule, what I want to do now is to go and find the derivative of this numerator function, which was 2x. Now, I'm sure everybody here understands how to differentiate 2x. That's one of the simplest one. You're differentiating 2x, you get 2. Now, if you know you don't understand it, you can always let me know. I can go back to that basic, but I thought probably that should be something everybody know. 2x, we're going to have the derivative as 2. Now, if I want to find the derivative of gx, this obviously will just be 1, because when you differentiate, it gets you 1. When you differentiate 1, it gets you 0. That'll be 1 plus 0, which is just 1. All right. Now, this is what we then do. You then go on to fix this back as like this was the numerator, this was the numerator, this was the denominator. So you're having a new function, so to say. That's L'Hopital rule. So you'll be having 2. In this case now, you'll be having 2 over 1 as the situation. And obviously, you don't even have an x value here. So if you go on to the limit of a constant, will give you the constant. All right. So in this case now, if you're having limit of x tending to infinity where you have 2 over 1, it's going to still be 2, which you can see give us the same thing that we have right here. So you can see the 2 different ways we use to solve this. We use the simplification way. This is it, simplifying it. We divided through by the highest power of the variable, that was x. That was this, we got 2. Now we use what we call L'Hopital rule. This is it right here. This tells you that you can use these 2 different methods, except if they told you to, you must use 1. So now we're going to solve many more questions now. This is the real deal for the day. So at the end, if you didn't understand it now, I believe at the end of this class, you should be very sound in using both of these methods. So let's try and get the rest of what we want to do right here. So we have now I just use this as an example. I'll be getting much more into L'Hopital rule when we are dealing with more of the circular functions. So more of the circular functions. All right. So I will give you these three different functions, and I would love you to use by dividing through by the highest power of the denominator, or sorry, of the whole function, the highest power of the variable, go on to give me the limit of this function as all of them, x is tending towards infinity for all of them. So let's move on from here. Let's see how you guys do in this. So we have this, you can start solving right immediately. You don't have to wait till I'm done writing all the other ones. Just keep pouring your answers so we don't have to waste time on this because we have many questions to solve tonight. So this is the first question. Give me the answer as x is tending towards infinity. All right. And we have 2x minus x squared minus 3x cubed over x raised to power 4 plus 2x squared plus 1. So just keep solving this, and let me get your answers in the chat below. Then we have 2x cubed minus 5x squared plus 1 over x minus 3 minus x cubed. So for all of these, x was tending towards infinity. So let me start getting answers quickly. Do we have answers already? So what's the very first answer? The very first question, number one, what did you get as the limit? Okay, so I don't know if you guys are flowing, but we can use both the simplification or the L'Hopital. I think I would love us to even start. Okay, I love this. Which one is zero? Okay, the first two is zero. So I would use the simplification method. I will use the L'Hopital so that I want us to build the L'Hopital from this, because very soon I will be getting into circular functions. And if you don't understand the simplicity of this one, you may not understand circular function. Okay, so let's try and use it. I'm using simplification now for the three of them. So you will note the answer, then we'll go on to use L'Hopital for the three of them. So for simplification, I'm to divide through by the highest power. So I have 3x squared. The highest power here is x cubed. That'll be over x cubed plus 5x over x cubed. You can see what I'm doing, minus 1 over x cubed. Just follow the step, you will never go wrong. Then I have 4x cubed over x cubed plus 2x over x cubed plus 6 over x cubed. All right. So what does this give me now? This will give me 3 over x plus 5 over x squared minus 1 over x cubed over 4 plus 2 over x squared plus 6 over x cubed. You can see the process. You can see the process, right? Now, what you want you to do then is to go on to fixing your value as infinity. So let's go on to fix as infinity. That will be 3 over infinity plus 5 over infinity squared minus 1 over infinity cube over 4 plus 2 over infinity squared plus 6 over infinity cube. Anything, all this will turn to 0, 0, 0, 0, 0. Everything will turn to 0 here. I told you anything over infinity. Once you're having over infinity, it's all 0. That will be 0 plus 0 minus 0 over 4 plus, because you can see I said anything over infinity, 0, 0, we just keep happening, plus 0. So this will be 0 over 4, which is 0. So the first one is perfect. I believe everybody got the answer there, right? So this is us doing simplification. Do you want us to quickly do L'Hopital rule for this, or do we move on to the second? Okay, let's do L'Hopital rule for this quickly. All right, let's use L'Hopital rule for this, then go on so that we don't miss. So you can see how this works. This is 0. So let me go on to use L'Hopital rule and let's see if L'Hopital rule will work also. L'Hopital rule, I told you already, states that when you have a situation like this, of course, if you go on to the reason why we did simplification, I missed that step. I should have done that before I went on. If I fix in theta x as infinity here, before you decide to use L'Hopital rule or simplification, we have to always investigate if it ended up as an indeterminate form. So if you go on to fix this directly, one of the things you would have gotten would have been that you would have seen it ended up as an indeterminate form. Imagine I fixed this directly. This would be, of course, infinity squared times 3. Infinity, I told you, all this will end up as infinity. This will be infinity over, this also will lead to infinity, which is literally what we call indeterminate form. So we don't want to have situations like, we can't deal with situations like this. So we have to use either simplification or L'Hopital rule. L'Hopital rule now is what I want to use because I've used simplification and you have seen we got the answer to be 0. So what are we going to do when we want to use L'Hopital rule? Very simple. What you have to do, now I told you, let's call f of x. Okay, let me do that right here. Let's call f of x. Let's call it this one on top. That's 3x squared plus 5x minus 1. All right. And let's call g of x, this one under 4x cubed plus 2x plus 6. I want you to see how L'Hopital rule works here. All right. Now, what I told you about L'Hopital rule is you want to go on to now find the derivative of each of the function, the numerator and denominator. This was the numerator, this is the denominator. So I want to go on to find the derivative now. I'll find the derivative of this. I'll also find the derivative of this. Now, again, if you know you don't understand this and you are having issues with understanding how to solve this simple derivative, maybe when we get out of here, we can talk about that. Now, look at it. We want to differentiate this whole function. You differentiate them individually. All right. So to differentiate this will be 2 times 3. That will be 2 times 3, that will be 6x raised to power 1. You know that you'll be multiplying the power by the coefficient of what you are differentiating, and then you'll be subtracting 1 from the power. So if I'm going to do that there, that will be 6x raised to power 1. Then I do the same for here. The power here is 1. That will be 1 times 5. That will still remain as 5. And then x raised to power 1 minus 1. 1 minus 1 is 0. That will be 5x raised to power 0, which is 5. So this is the answer for the derivative of the first of the numerator. Let's do for the derivative of the denominator. Look at it. We have 12. I don't think I want to be spending time to be. I think this is something everybody should know already. So this is the derivative for this. I'm sure you all agree with this. This is the derivative we're going to get when we differentiate the denominator. All right. Now, what do we do next? You will now turn, this will now be your new fractional function. So now you want to find a limit as x is tending towards infinity when you have 6x plus 5. When you have 6x plus 5 over 12x squared plus 2. So you want to try this again. Now, you have done the first derivative. This is L'Hopital rule we are doing, don't forget. This is L'Hopital rule we are doing. Now, 6x plus 5 is, we want to fix in x as infinity. So we have 6 times infinity plus 5 over, everything I'm doing right here will help you in all the other things around circular functions, because if you don't understand it with a simple function, you will have issues otherwise. So this is another example where we have 6 times infinity, it will always be infinity. So we have infinity plus 5, which is the infinity over infinity. Can you see what's happening right here again? So now we are still having an indeterminate form. Now, L'Hopital rule states that you can keep on following the same process if you are still getting the indeterminate form. So we differentiated now and we still get indeterminate form. So what you have to do is to differentiate again. So you go on to differentiate again. That's the basics of L'Hopital rule. So now what we want to do next is to differentiate this next, the next thing we have done. So let's differentiate this. We want to differentiate this again. That means the denominator won't differentiate the denominator again. So we are having the second derivative now of the numerator, which will give you the value of, in this case, differentiating this again will just give you 6. Whereas we have that for the denominator, the second derivative, we have it as what? This will be 24. Don't forget, we're dealing with indeterminate functions. So since we got indeterminate function again, we have to go back and differentiate again. Now we can go on now to do this same thing again. We will go on to now try to find the limit. We'll try and find the limit now as x is tending towards infinity of this new one now, 6 over 24x. You can see the stages, and this is introduction to L'Hopital rule. So when you are seeing this elsewhere now, you know exactly the process. All right. Now, I can see somebody talking about taking too much question on the time. This is basically what you need in order to solve. If I get into circular function now, at this rate, we are not slow. This is the process you have to go through for you to be able to really understand the other things. If I start bombarding you with complex expressions and you don't understand what's going on, you will start to complain of not following. That's when you guys will start saying you can't follow, you are saying things differently and everything. I want you to understand the basics first before we go on to those things. And if you have a problem with that, you can check out of the class, all right? Now, what we have right here now is 6 over 24x. So you want to go on to fixing x as infinity. Now we have 6 over 24 times infinity. Now we have 6 over infinity. Now look at this. This is going to give you the value 0. And this is where you end your answer. All right. So you can see now that the process of L'Hopital rule can sometimes take different stages. So if you are asked to use L'Hopital rule, ensure you take your time. All right. All right. You see, for these other questions, we have the same process will apply to both number 2 and number 3. I'm sure you guys have been able to find everything around when you use simplification and when you use L'Hopital. No, you probably have not done L'Hopital rule. Maybe I'll give you this as an assignment. Investigate L'Hopital rule using this and using this. All right. So the process have been concluded on question number 1. Use L'Hopital rule for question number 2. Use L'Hopital rule for question number 3. And let's see if you get the same answer. Now, I want to move you now into situations where you'll be having circular functions. And in this case now, you need to understand all the identities, both of trigonometry and that of differentiation. If you don't know the identities around both trigonometry and differentiation, you would have serious issues here. All right. Now, look at, I will just put a few here, some of the identities I think you should have already, because some people will say, how am I getting this? How am I getting that? If you have your function as these values I'll be writing here, you have sine x, if you have cos x, I will just write a few, and I would hope that you have it somewhere. And if you don't have it, you can let me know so I can write them in full. So all these things are very vital when you are solving questions around trigonometry. All right. You need to know the derivative. That means what will happen if I differentiate sine x? That means we're dealing with the y over the x, as many people will prefer to say. What's the y over the x when my y was sine x? Now, these are not things that you want to go out there and be racking your brain on. They are all available for you. So you just have to ensure you note them. All right. Now, now we have, if you have sine x, the differentiation will be cos x. All right. If you differentiate sine x, you get cos x. If you differentiate cos x, you will get minus sine x. If you differentiate tan x, you will get sec square x. If you differentiate cosec x, you should get, I'm not sure about this, but probably I'll get back to you on this. But let me write some other ones like cos sine ax. If you have sine ax, you have a cos ax. Look at this experience now. When you have this, let me try and just give you a brief around this. When you have, for instance, you have sine x. You have sine 5x as your function. Now, if you're trying to differentiate this, you want to have it as 5 cos 5x. You notice if I wrote this as my answer when I differentiated this, you don't need to wonder what went on. All that happened was that I just followed the rule around the identities. That when I have sine of something like this, this is the value. This is what I'm going to get. So many of you, your confusion will come from you not understanding these identities. All right. And that's why I would love you to have them handy so that you can always, so you can, you're going to be having it as a, because now we have a constant here, it will be a sec square ax. So on and on and on, there is there is so much identities, we cannot write them all. I want us to go on to start using them. So just what I will ask you to do is, if you have them somewhere, please, you can open it right now, because you'll be needing them right now. We want to see how to, we want to get into using them. So majorly we'll be using both methods. We're using both we'll be using both we'll be using both methods, simplification method and also the L'Hopital rule. All right. Now look at the very first question we want to answer. Of course, let me give you this question, and I'm sure you know what to do here. Imagine I have this question and I have limit of x tending to 2. How do you solve this? All right. How do you solve this? Now, we can use both the L'Hopital rule and the simplification rule. I will use the simplification rule very easily. And in this case, I want to simplify by factorizing this. So I have x squared minus 4. I'm sure you can see this is the same thing as x squared minus 2 squared over x minus 2. Now, if I have x squared minus 2 squared, it's these are not things I think I want to spend too much time on, because I expect you to know that this is going to be the same thing as x plus 2 and x minus 2. Now we have over x minus 2. So of course, you know, this will cancel this. Now, before I go into this, let me tell you the reason why I'm trying to simplify or use L'Hopital. I should have made the attempt initially. Don't mind me, I omitted that. If you are given a question, I told you the first thing to do is to first insert the value inside. So what I was supposed to do initially was to have 2 squared minus 4 over 2 minus 2, because x was tending towards 2. Now I have 4 minus 4 over 2 minus 2. That was 0 over 0. This is another indeterminate form, which I told you will always lead you to using either the L'Hopital rule or the simplification rule. You can solve this by either simplifying or by using L'Hopital rule. I'm trying to simplify right here, which you can see. Look at what we have here. So I'm trying to simplify it. By simplification, I'm able to get this function to limit x tending to 2, x plus 2. Now, after simplifying now, I can now go on to fixing the values for x as 2. Then we have 2 plus 2. That will be 4. This is the answer. All right. So I don't want us to just use simplification, because it's very possible they would specify you use L'Hopital rule. So if they specify using L'Hopital rule, you cannot use the simplification method. So let me quickly go on to use the L'Hopital rule. So after getting 0 over 0 as my answer initially, and I discovered that this is an indeterminate form, what I want to do next is to try and using L'Hopital rule, I want to find the derivative of both the numerator and the denominator. So the f of x now is equals to x squared minus 4, and the g of x is equals to x minus 2. If I want to find the derivative of this will be obviously 2x. If I go on to find the derivative of this other one, this will obviously be 1. So I want to now go on. Of course, you know, this will be interchanged for both the numerator and the denominator at this point. I'm using L'Hopital rule, don't forget. So I want to find the limit as x tending towards 2. Now, no longer using this one, but this 2x over 1. All right. So I fix in 2 now into the expression. That will be 2 over 1. That will be 4 over 1. That's 4. So you can see that using both the simplification method or the L'Hopital rule will always work. All right. Now, let's now get on to circular functions, and then you will see how the use of all the identities, both trigonometry, will be very, very important. All right. You will need to, if you have issues with your trigonometry identities, you may have serious issue in being able to solve questions under calculus, because calculus entails calculus has a lot to do with trigonometry, especially the identities. So let's say we have this function. Now x is tending towards 0, and we have tan 2x over 4 sine x cos x. All right, look at the function we are given. We're given, for somebody asking about secant ax, we have a lot of identities. They are all there. I just did not want sine secant ax is equals to a secant ax tan ax. That's the derivative. But you can go on to get all this. If you don't have it somewhere, maybe I will share a whole lot with you probably later today or probably tomorrow. So they are all identities there. You should have a textbook and have all these things written somewhere. There's a lot of them. It's not just the few I wrote. And you have the same thing also for integration. So you should have both for differentiation and both for integration. Now look at what we have right here. These are the kind of questions that used to give students a lot of problem. All right. We have something like this, and we're told to find the limit as x is tending towards is 0. The first thing you want to do, I told you already, is first of all, fixing your value of is 0. All right, fixing your value for is 0. If you push this on a calculator, in the end, you will get is 0 over is 0, which is another example of what we call indeterminate form. All right, indeterminate form. Now, if you have this as your result, I told you already, you can use two different methods, L'Hopital or simplification. So I would love us to use both methods and ensure that we can perfect anyone we decide to use. Now I'm going to use simplification first, because for this question, simplification is probably easier. So let's see what we can do. If I want to simplify this, because I know my identities, if you don't know your identities, again, I told you, there will be issues when you are solving circular functions. Because all this tan 2x, like, look at what I can see now. You see this thing we have here, this denominator now, we have, look at the denominator. The denominator was written as 4 sine x cos x, right? You can see the denominator written as 4 sine x cos x. Now, because I know my trigonometry well, I know that this can also be written as 2 times 2 sine x cos x. And I remember carefully that under trigonometry identities, I know that this looks like something I've seen somewhere. And this looks like what we say is sine 2x. If you go back to your compound angle, double angle, this is double angle. Sine 2x is equals to this. So that means instead of writing this whole 4 sine x cos x, this is what I'll be writing now. Do you see exactly what I'm saying? You need your trigonometry identities here a lot. Look at tan 2x. Because I know my trigonometry identities, I can easily write tan 2x as equals to sine 2x over cos 2x. All right? I can write it like this. Now, if I go on to try and bring all this together, that means this limit of x tending towards 0, we have sine 2x over cos 2x. This will be divided by, so I can write it as this, divided by what we have here. Instead of writing this whole thing, I'll be writing just this. 2 sine 2x, of course, over 1, because we don't have, but just leave that there. So we can have it as limit of x tending towards 0. I have sine 2x over cos 2x multiplied by 1 over 2 sine 2x. Now, look at this. Now, I'm sure you can see that, obviously, sine 2x can cancel sine 2x at the denominator. So this right here can cancel this right here. So this will result in having the limit of x tending towards 0, 1 over, this is 2 right here, 2 times cos 2x, that will be 2 cos 2x. All right. Now, you can go on now to try and fix in the value for x as 0. Don't forget, all we just did was to simplify. I told you we have 2 different ways of solving questions like this. After we got an indeterminate form, we can go on to simplify the function, which is what we just did. You see, we went on to simplify the function, applying our trig identities. We simplified it, we got this. Then now we can go on to fix in the x as 0, whatever x was tending to. X is tending towards 0 here, so I fixed 0 here. I have 1 over 2 cos 2, wherever I see x, I'm fixing 0 now. If you go on to have this, let me write this here. This will be 1 over cos 2 times 0, that's cos 0. Cos 0 is 1. If you go on and check your calculator, cos 0 is 1. That will be 2 times 1. That will be 1 over 2, which is your final answer. All right. So you can see exactly how you solve this. This is using simplification method. Now, what if you are told to use L'Hopital rule to solve this? How do you solve this? Because of time, we will just go on to clean this up. All right, so we have to go on to use L'Hopital. Now, using L'Hopital rule, I told you using L'Hopital rule, what you have to do, very simple. Go on to differentiate the numerator, go on to differentiate the denominator, and then use it as a new function. So what I want to do now, using L'Hopital rule, is say, what is my fx? My fx is, that's the numerator, tan 2x. I'm always terming the numerator as fx, denominator as gx. So this is 4 sine x cos x. This is very vital. Again, I told you, we're going to be learning so much in while we're trying to use L'Hopital, because in some cases we'll be using product rule, in some cases we'll be using chain rule. So it's all mingled together. So as much as we're trying to find L'Hopital, find the limit using L'Hopital, we will also be getting to solve we'll be getting to solve it using several methods under calculus. Now, look at, I want to find my derivative for tan 2x, because that was my fx. So I want to find the derivative of tan 2x. Now, this is why I said you need to know all the identities that we have been talking about. If you go on to check the identities that I gave you now, I don't know if I gave you this. I probably did. If you have tan x, the derivative is that if you are trying to differentiate tan x, what you should get is, tan ax, because this is a situation around tan ax. So tan ax, if you have tan ax or a form of tan ax, examples is tan 2x, tan 4x, tan 5x, or whatever. If you have a situation like that, what you want to do is go on to have a sec square ax. All right. So this is the basic identity around this. So I'm not doing anything different. I just want to apply this identity. So when I have tan 2x now, my derivative will be, of course, a here is 2. That will be 2 sec square ax 2x. All right. And when you have this other one, you want to differentiate this function. Look at what you have right here. Now, how do we differentiate 4 sine x cos x? So I told you already, you will learn so much around this. Now, what do we use here? I can decide to use something which let me use 2 different methods to solve this. Look at it. I want to find the derivative of this. Guys, make sure you're paying attention, because this could actually just be an objective question alone. Find the derivative of this. So as much as I know I'm trying to solve L'Hopital rule here, don't forget that we are also learning something around finding the derivative of circular functions. Now I have 4 sine x cos x. How do I find the derivative? Number one, I want to use 2 different methods. Any one of your choice you can pick. The first method will be me trying to simplify this as, so I want to write my g of x rather than writing like this. I want to write it as 2 times 2 sine x cos x. I want to first simplify the g of x. Then I want to write this as 2. All this now will turn to 2 sine 2x. Do you see that? So if I want to find g of x derivative, all I want to do right here is just apply the rule around derivative around sine ax. Now, we already said remember what I wrote? I wrote that if you have sine ax, let me write this right here. If you have sine ax, the derivative is always going to be a cos ax. All these things are not something I'm asking you to, you don't need to ask me how did I get this. This is an identity under differentiation, that when I have sine ax, the answer for my derivative will be a cos ax. I wrote a few of them some minutes ago. So sine ax, this is the response to that. Now I can see a situation like that here because I can see I have sine 2x. All right. So when I want to find the derivative of sine 2x, of course, don't forget there's a 2 here, which you will maintain. I'm trying to find the derivative of this whole thing. I want to find the derivative of this whole thing. So this will be 2, of course, multiplied by, what's the derivative of this now? This will be 2, here is represented by 2 cos 2x. You see that I'm differentiating sine 2x. Differentiating sine 2x is 2 cos 2x. There was a 2 there before, so you maintain that. So the final answer for the derivative of this will be 4 cos 2x. So you can see how easy that is. So obviously, I've gotten, using this my first method, my derivative of my gx to be 4 cos 2x. All right, this is nice and simple, but there's another method some people may prefer to use. Let's try and use that method. So imagine you have this and you did not want to even simplify it further. You just wanted to use it the way it is. Let's see how to solve that, because there may be a case where, let me say this, there may be a case where you may not be able to identify a trigonometric identity, which was how we were able to get sine 2x. So how do you solve a situation where you have 4 sine x cos x? It could be something else. That, imagine it was 4 sine 2x now. You know, in that case now we will not be able to change it to this. So let's see how we're going to do that. So we're going to solve this g of x again using a different method, and we must arrive at 4 cos 2x. All right. Now, How do we get this? Look at using what we call product rule. Product rule identifies that in this case now we are having g of x as a product of two different things. We have 4 sine x as the first part multiplied by cos x as the second part. So this is how, some people will ask me, how do I know what rule to use? It's based on what you can see. When you see a product of functions, this is 4 sine x times cos x, which is what gave you this. When you see a situation like this, you want to apply what we call the product rule. What is the product rule? The product rule states that when you have, when you want to find the y over dx of something like this, let's say this was, or let me just use the g over the x for you to understand better, because now we're not using y as our function. The g over dx in this situation will be equals to u dv over dx plus v du over dx. This is product rule. That when you have a situation like this is how you solve it. All right? A situation like this, you solve it this way. Now, this means we have to call the first part of this thing u. So our u here is 4 sine x. And our v here is cos x. Product rule. Probably we'll still go more into this later, but just for the sake of understanding this, when you have a function that is as a result of two products, you can see this times this, then you apply product rule. This is the first side of things, which we call u. This is the second side of things, which we call v. So u and v are very important for us to get our final answer, but we also need the v over dx and we need the u over dx. So let's now go and find what is the u over dx now. The u over dx, looking at what we have here. Of course, product rule, when we have our differentiation identity, when we have sine x at cos x, so we're trying to differentiate this function. This is a simple function. This one is not complex at all. So I want to have 4 cos x as my answer. Somebody say, how did I get cos x? It's all in the things I wrote for you before. When we are dealing with differentiation, if you have the sign of anything, if you differentiate it, you will get cos x. If you have the cos of anything and you are trying to differentiate the cos of something, you will get minus sine x. You should know this. It's basic. All right. So now we have been able to get the u over dx. We also need the v over dx. So the v over dx, very, very important. All right. How do I get the v over dx? That means I want to differentiate my v. That's the meaning of the v over dx. If I differentiate my v, what do I get? I just wrote it here. The cos of x, if I differentiate it, I will get minus sine x. All right. Now, good. So I have been able to bring out all the elements of my product rule. I have gotten u, which I knew initially as 4 sine x. I've gotten v, which I knew initially as cos x. I've gotten the v over dx, which I got as minus sine x. I've gotten the u over dx, which I got as 4 cos x. Now that you have done this perfectly, what you want to do next is to bring them all together. So the differentiation of these two things, the product of these two things, which was g of x, will be when you will have to apply all this. So the g over the x will be equals to, what is u? 4 sine x. What's the v over the x? The v over the x is this. That will be minus sine x. Look at how I'm fixing this properly. This is u, the v over the x. Don't forget we're using du dv over dx. Then plus v. This is v now, cos x. Then du over dx, which is 4 cos x. All right. So this is my result. Now, if you go on to bring this all together, you will see that you will be having your final answer to be minus, this will give you minus 4 sine square x. I'm sure you know why, because this is sine x, this is sine x. Sine x times sine x will give you sine square x. And then we have 4, and then we have the minus, plus this will give you 4 cos square x. Let's try and make this in such a way that it looks much better. So I can write it rather, let me write it as 4 cos square x minus 4 sine square x. All right. Now, with what I have right now, I can do something also. I can factorize 4 outside, and I will have my cos square x minus sine square x. Now, look at why I said you need to know your identities. Do you remember this is an identity? I don't know how many of you can remember this is an identity on trigonometry. That when you have the cos square of an angle minus the sine square of the same angle, it is something we call cos 2x. That's cos 2x. That's cos 2x under trigonometry. It's always cos square x minus sine square x. This is a basic identity, double angle, under double angle, or under trigonometry. So that means I can go on now to, for my g of x. Don't forget, this was the gx, which we've gotten here. I can write this now as 4. Instead of writing cos square x minus sine square x, I can write it now as 4 cos 2x. So you can see we got the same answer. So we used both methods. The method we used before and the method we used, the product rule, we got the same answer. Now, that was just for us. So we have been able to get, we're dealing with no longer tan square x now. We are dealing with 2 sec square 2x over 4 cos 2x. That's the new thing now. And looking at this, I'm sure you agree with me that it is better, because I'm sure you guys we don't have so much that has to do with sec on our calculator. So it is better for us to simplify this further. When we have this sec square 2x, let's make it, of course, I'm sure everybody remember. I told you already, if you have issues with your trigonometry identities, calculus will be very, very hard, especially circular functions, because you really need them. Look at this case now when I'm having sec square 2x. Sec square 2x. I want to use this my identity, which told me that sec of an angle is equals to 1 over cos of an angle. So if you don't know that, of course, there's no way you want to solve this much easily. So I want to, instead of having sec now, I want to have 2. Now I will be having 1 over cos square. Don't forget, because we're dealing with square now. It's like if sec x was equals to 1 over cos x, obviously, if we just go on to square, that's the meaning of sec square 2 sec square x. So sec square x will be equals to 1 over cos square x. So, but in this case now we're dealing with x. So we just have the 2x here, and we have over everything over 4 cos 2x. All right. Now this will be the limit of x tending towards 0. Then we have 2 over cos square 2x divided by 4 cos 2x. So because of space, I will just change this right here to be multiplied by 1 over 4 cos 2x. All right. And looking at what we have here, this will be the limit of x tending towards 0. And I have 2 over cos square, no more square, because cos square 2x times cos 2x will be cos cube. I believe you understand that. Cos square 2x, if we have cos square 2x and we have cos 2x, that will be cos cube 2x. All right. Cos cube 2x. You can see exactly what I'm saying. This is serious work when you're dealing with circular functions. You have to be very solid with trigonometry. Once you have issues with trigonometry, you almost don't stand a chance to solve questions around this, because every single thing you'll be applying identities. So now that we have, of course, I should not forget my 4 here. There's a 4. Yeah, there was a 4 here. So we can go on now to, of course, put in our values for x being 0. So I have 2 over 4 cos cube 2 times 0. So if you go on to find, this will be obviously 2 over 4 cos cube 0, because 2 times 0 is 0. So if you are having an issue with trying to solve this, just say 2 over 4, then have cos 0 all raised to power 3. That's another way of writing this. So if you don't know how to find cos cube 0, just find cos 0 and then cube it. So what is cos 0? Cos 0 is 1. So that will be 2 over 4 times 1 raised to power 3. And that will obviously be 2 over 4. Which will be what? 1 over 2. Was this not the same answer we got when we simplified it? Of course, yes. We go on to the previous, when we decided to simplify, the answer we got was 1 over 2. When we use L'Hopital rule now, we also got 1 over 2. What was the basics of L'Hopital rule? L'Hopital rule states that when you have a situation where you arrive at an indeterminate form, what you have to do next is to find the differential equation or the expression for the numerator and that of the denominator. So this was the numerator, this was the denominator. We went on to differentiate this, we got this. Went on to differentiate this, we got this. Then we fix this now as the numerator, fix this now as the denominator, and then you insert your limit at that point and check it again. Now, if you check, if you fix in your x tending towards whatever it was tending to, in this case 0, into that expression, if you discover that you still get an indeterminate form, as I did earlier, what you have to do is to go on and do the differentiation again. So you are permitted to keep differentiating until you get to a result that is not indeterminate. So this is how you solve L'Hopital, expressions using L'Hopital rule. So let's run into another question. This one very simple. Let this be like something that will give you guys. How? By the way, let me get feedback. How do you guys feel about what you're solving? Are you comprehending it? Let me get some feedback from the class. What do you guys feel? What do you guys feel? Because I want to know. I hope you are not having issues because of the trig identities, which I believe some of you may have forgotten. So what's your response concerning your understanding? Are you understanding? Did you understand what we have been doing? These are the kind of questions you will see. You see lots of questions like this. Okay, some of you are getting, okay. Oh, somebody said, some people said they are not. Okay, somebody said brain is not brainy. Or somebody said it's sinking. Okay. Okay, you see, this is the reason. You remember when I was saying I wanted to establish the basics? It's actually because I know what was coming. Yeah, exactly. That's what you see. I started by saying the trig identity is quite very important. If you don't know trig identities, you would have very serious issues, because it's like the basics around circular function. You cannot solve circular function without good knowledge of trig identities, because at any point in time, you could just get to a place where your knowledge of trig identity is what will give you the understanding of what you do. So that's why I always encourage you, go and learn your identities very well. Now, look at what we have here. So those of you that you're giving me the answers of these as one. What did you use? What method did you use to solve? Okay, guys, I would love you to drop your names if you are present in this class. Please drop your names very quickly. Just drop your names at this point. So the guy want to. Okay, now let's drop your name quickly and let the attendance be taken. Now, we have this question, very simple question. What we have to use is L'Hopital rule, obviously. And when you see this, before you decide to use L'Hopital rule, guys, I told you one thing. First of all, test the limit. Now we have x tending towards 0. So I want to say first sine 0 over 0. And what I will be getting here is obviously not pretty, because this is not going to give me what I want. So I want to go on to use L'Hopital rule now. And I told you, L'Hopital rule, first of all, you have the numerator as sine x, and you have the denominator as what? X. So L'Hopital rule states that find the derivative of both of this numerator and denominator. So if you differentiate sine x, you get cos x. So my derivative of f of x will be cos x, and my derivative for g of x will be 1. All right. So what I want to do now is to fix this as a new function. So I want to have the limit as x is tending towards 0 now of cos x over 1. So if I fix this 0 now, cos 0 over 1, this will give me 1 over 1. That will give me 1. Now, let me state this. What I just wrote for you is quite very important. So note anywhere you go from what we just did, because we will be needing this later, that the limit as x was tending towards 0, when we have sine x over x was equals to 1. We have proved it already, right? So this is not something that I think you don't, you can obviously see it right in front of you. So let me see how you fare with this. Secular, of course, those of you that said you didn't understand, you got lost because of the trig identities. The secret to solving this now is to go on to, first of all, go back and revise your trig identities. That's the key. Look at this question, which I believe will be the last for the night. We have 2 tan x minus x cos x over x plus sine x. All right. Can you go on to find the limit of this? So the first thing you want to do, as I said already, is you want to go on to this was, I wanted you to note this. Please note that the limit of this is 1. The reason why I'm saying this what I wrote right here now is because very soon you will see a situation where, guys, that's why I said you should pay attention. You will see a situation where this thing will come up in one of your expression. Now, in that case, you don't need to go on to be solving that again. But of course, if you don't know it, you would have had to solve it again. But if you knew it already, or you would just do is just to fix in 1 as the answer. So look at the answer right here. We have 2 tan x minus x cos x over x plus sine x. How do you solve this? What's your response to this question? Of course, the very first thing you want to do, I told you before because it's not every expression that will give you indeterminate form. In some cases, it will not give you indeterminate form. So how do you check for that? 2 tan 0 minus 0 cos 0 over 0 plus sine 0. This will obviously be, you go on to do all this, this will give you 0 over 0. So obviously it's resulted in an indeterminate form. So we don't want to, we don't, I don't know, you can use whatever method you want to use, but I would love to use the L'Hopital rule. All right, L'Hopital rule seems to be the most visible method here. Of course, if you are ready to do a lot of trig expressions, the simplification will also still work. Now let's go on to try and do the L'Hopital rule, and I'm sure you guys will gain a lot. You know, I told you, you're not just learning L'Hopital rule, you're also learning all this derivative. You're learning how to solve circular functions. So you are getting several things in this particular class. So let's see how to try to solve this. So now, I'm sure you agree with me that if I want to use L'Hopital rule, since I've confirmed that it arrived at indeterminate form, I want to go on now to say, what's my numerator? That's my f of x. And I said my f of x was 2 tan x minus x cos x. What's my gx? My gx is x plus sine x. All right. Now, what is the derivative of these two different things we have here? So this is where you have to work. The main work for your L'Hopital rule will not majorly be in solving it. It's majorly going to be in getting the derivative of these circular functions. So now look at these two things. Now we want to go and find we want to find the derivative of the function, the numerator. I want to find the derivative of the denominator. All right. Now, let's try and start with the numerator. So look at the numerator. The numerator is quite interesting. We have 2 tan x minus x cos x. So the first thing is, because we have more like an not algebraic now, so to say, but we have addition and subtraction of two different expressions. So we can solve for the derivative of this, then solve for the derivative of this. I'm sure you understand what I'm trying to say there. So if I want to find the derivative of this, I can differentiate this, then differentiate this, then add or subtract, whatever you are doing there. So in this case, you are subtracting. So I want to find the derivative of this, and then find the derivative of this. Then I will subtract them. I will use the whatever divided them from each other. That was subtraction. So I want to find what's the derivative of 2 tan x. These are not things that you need to sit down there and be racking your mind on. It has been given already. We told you already initially that when you have tan x, the derivative of tan x is sec square x. So I have 2 tan x here. I owe the 2 here, and I just write sec square x. Simple. I have differentiated the first part. So I want to go on to differentiate this other part now. Now, this one is not as easy as this other first one because it is made up of two different expressions now, and we would have to use the product rule because this is a very important application of product rule. You can see this one was simple, 2 times this, which we can arrive at this easily. But you know, in this case, have two different expressions, x and cos x. So we cannot just go on to say we want to find derivative of x. It's not plus separating them. If it was plus separating them here, you would just go on and say what's the derivative of x, then what's the derivative of cos x. It is times. So you have to use product rule. Does it make sense? You have to use product rule now to express it. So I will leave this space. Let me leave this space and I will not write anything in this space. So this space will be whatever I get as the final answer of this. That's what this space will be for. Let me go on to find the derivative of this one. I'm still trying to find the derivative of the numerator. So let me find the derivative of x cos x. So I want to differentiate x cos x now. When you look at this now, this is divided into two parts. This is my u, this is my v. So u is equals to x and v is equals to cos x. I'm sure you guys can flow. This is two different substances. So this is my first, this is my second, x cos x. So product rule, which I told you already, is that if you want to find product rule, this is just basically product rule. What you have is u dv over the x plus v du over the x. These are the things we want to solve. So I've gotten u, I've gotten v. I know u, I know v. Based on what I have here, this is u, this is v. So I want to go on now to find the u over the x, and I also want to find the v over the x. So once I'm able to find the u over the x and the v over the x, I'll fix them into this product rule and I will achieve my final differentiation of this whole thing. So now what is the u over the x? The u over the x when I have u as x is just 1. If I differentiate the u here, I will just get 1. If I differentiate the v over the x, this is a circular function where we have cos x. Under our identity, when you have cos x, the derivative is minus sine x. All right? Minus sine x. That's just basic. It's not this, what I just did now is not coming from anywhere other than I went to my identities and I used it. I was told that whenever I see cos x in differentiation, if I want to differentiate it, I will get minus sine x. So that's all I just used here. So I've successfully gotten both my u, v, the u over the x and the v over the x. So I can use my product rule now. My u is x. So that will be x times the v over the x. That will be minus sine x. And then plus, I'm applying this rule. V is cos x. That will be cos x. Then times the u over the x. The u over the x is 1. So what I have here is minus x sine x plus cos x. So that was the answer to my differentiation of x cos x. Can you see now? This is the answer to x cos x. This is the answer right here. This could only be an objective question. They said find the derivative of x cos x. This is the answer to it. All right. So now I can go on now to fix this answer here. Now 2 sec square x minus. So I want to have. I'm using my bracket because this is a complex. This is not just a simple expression. So I want to ensure I use my bracket here. Minus x. I'm fixing odd derivative of this. Minus x sine x plus cos x. All right. So now I've gotten this. Of course, my final derivative here. Let me rub this up. I can bring it out as 2 sec square x plus x sine x minus cos x. Do you see that? So this is the final answer for the differentiation of the numerator. Good. So let's go on to find the final answer for the differentiation of the denominator. That is the process you find for both, and then after you're done finding for both, then you use the L'Hopital rule to solve it. Now, for gx, if I want to differentiate this, this is two different things separated by addition. I differentiate this, I will get 1. 1 plus what? When I differentiate sine x, what do I get? You get cos x. That's not something I'm manipulating somewhere. I told you already, this is your identity. So just make use of your identity. That's all. So now we're getting the derivative for my numerator. I've gotten the derivative for the denominator. So I can now go on to, don't forget this was the limit. We are looking for the limit of x tending to 0. So I'm using now this as my numerator now. I'm having it as 2 sec square x plus x sine x. That's my numerator derivative, cos x, over my denominator derivative now, 1 plus cos x. All right, this is L'Hopital rule now. So now, what you want to do next now is to fix in the values for x as 0. But you see this sec square x, it's not just nice to see it there. So I want to rather change it to, as I said already, you need to know your trig identities. I know that sec x equals to 1 over cos x. So obviously sec square x will be equals to 1 over cos square x. That's 1 square over cos square x. So obviously I can change this to, okay, let me use this. I can change this to limit of x tending towards 0. Then I have, instead of writing 2 sec square x now, I'll be writing 2, of course, times 1 over cos square x. That's sec square x, which is, I can just write this as 2 over cos square x plus x sine x minus cos x. Everything over 1 plus cos x. All right. Now you can go on now to fill in the values for x as 0, because you are having sine cos now, which is easily, you can easily punch that on a calculator. So fixing x as 0 now, what do we have? We have 2 over cos square 0 plus 0 sine 0 minus cos 0. Everything over what? 1 plus cos 0. So you can go on to push this on a calculator now and start seeing what you're going to get. Of course, if you push this on a calculator, let's use this side. If you push this on a calculator, you'll be having, this is just like, those of you wondering how to push it on a calculator, cos square 0 is the same thing as cos 0 all square. It's the same thing as writing cos 0 all square. All right. So you don't need to, you just press cos 0 on the calculator, you get 1, then that's 1 square. So this will be 2 over 1 plus, of course, 0 times anything will be 0, plus 0 minus, this will be minus what? That will be minus 1, because cos 0 is 1. So this will be minus 1. Please don't say cos 0 is 0. Cos 0 is sine 0 that is 0. Cos 0 is 1. So this will be minus 1 over 1 plus, cos 0 is 1. That will be 1 plus 1. All right. So this will be 2 over 1 plus 0 minus 1. That will be 1 over 1 plus 1, 2. So the final answer is 1 over 2. This is exactly the theory around limits. So one of the basic thing here is that you're dealing with circular functions, and when dealing with circular functions, you will need your identity, and your identity play a very key role. All right. I want to give you this as an assignment. Let me see how you fare with it. So if you are aiming to excel in calculus, you have to very much be ready to patiently solve all these things. And the key is, number one, you have to know all the important identities. You will see situation where we'll be using the sum and difference formula. That will be tomorrow. We'll be doing some of those things tomorrow. When we use the sum and difference formula, and you would have to remember those laws under trigonometry. And if you don't remember them, you will just get stuck. Basically, that's the hard truth around calculus. It's very easy to be lost. Extremely easy to get lost in calculus. So everything I'm doing right here, you can see how basic they are, how simple they are while I'm solving it. Of course, that's because I'm applying all the identities rightly. So once you have an issue with the identity, for instance, let's say you do not know that sec x is 1 over cos x. That simple thing will get you hooked at this point. And if you don't know how to make use of all your differentiation and techniques, the product rule, the chain rule, and all these other things, it will bring lots of issues. So what I'm just going to advise you is coming to class tomorrow, try and revise up on trigonometry identities, and try and also revise the differentiation identities. Probably you should even have a note that itemizes all the identities from sine x to cos x to tan x to sec x and everything. Just try and write everything somewhere and start to put them into use, so that when we come to classes like this, you are not lost. All right. So what's the feedback? What do you guys feel about your understanding level? Let me know, and let me know if there's something you would want me to start with tomorrow. Let me get your feedback quickly. Where are you at in understanding this? Is it very clear? Are you understanding what we're doing? What is your understanding of this? This is calculus, and we would be going deeper and deeper and deeper. And if you get lost at this point, then it's very, very possible that you may have some issues furthering it, because this is basic, right? Okay. All right. So hopefully before around 2 p.m. Of course, we're getting to integration. Those of you talking about integration, we're going to get to integration very soon. And but we can't run into integration right now. You need to understand this very much, because integration and differentiation, they are both interwoven, and they are just the same thing. You differentiate, you integrate, you come back to it's all interwoven. So if you integrate, you get something. If you differentiate, you get something. It's all together, and the application is very easy. The application of both differentiation and integration is very easy once you understand this part. So this is the major part I want you to get along with, and then we can go on to applications, which is the key. So guys, we would continue tomorrow, the same time, 8 p.m. And please try and revise your identity so that you are not lost in the class, right? So please, this is a forerunner for your exam. So ensure that in your whole O2 exam, you're going to smash it. Please ensure you smash your whole O2 exam. This is the reason why we're doing all this. The videos will be released around 2 p.m. tomorrow, 2 p.m., 3 p.m. latest. You should get the videos, this particular video, so you can go back to revise everything we just did. So guys, thank you for joining. We'll see tomorrow. Take care of yourself.